This is problem 45, and in problem 45 we want to find the electric field at each of the indicated points. The distance between each sodium ion and chloride ion is 2.82 times 10 to the negative 10th meters. And just like we did in lab, I'm going to say that one block has a width A. That makes A equal to 1.41 times 10 to the negative 10th meters. They're asking us before we begin to sketch the direction of the electric field at each of the three indicated points. So if I'm at point A, the two closest charges are a negative charge and a positive charge. The electric field points towards negative charges and away from positive charges. So for both of those electric fields, it's pointing to the left. So when we add all four together, it's still going to be pointing to the left because the contribution from this charge and this charge are much smaller. For the same reason, at point C, the electric field is going to be also pointing to the left because it points towards the negative charge and away from the positive charge. And at point B, I'm closest to this positive charge and this negative charge. The electric field points away from the positive charge and towards the negative charge, and we can ignore the other two charges for now because the contribution is much smaller. So overall, the field would still be pointing to the right. Then we are asked, how should the electric field at point A compare to the electric field at point C? Well, we just saw that the direction was the same, and by symmetry, the magnitude should be the same also, because if you take your paper and flip it upside down, you have positive, negative, positive, negative. C is here and A is here, which looks like what you have when the paper is this way. Now you have negative on this side, so it goes negative, positive, negative, positive. So rather than this pointing to the right, it points to the left, just like A does, but the magnitudes are the same. Okay, so they have the same magnitude and they also point in the same direction. So the electric field at point A should be equal to the electric field at point C. If they ask you a question like this, before you answer the question, there's probably a good reason for it. If you can answer the question successfully, it might save you a little bit of work later on. Because we know the electric field at point A is equal to the electric field at point C, I'm only going to calculate the electric field at one of those 2 points, and then I'm going to say the other one is equal by symmetry, and that's what we set up here. Okay, so now I can go on to the mathematical analysis. The superscript 2 here means that the answer is given to you in the back of this section. So if you turn to the last page of the electric field or go to the last page of the PDF file for the electric field, here are selected answers. This is problem 45. Because it's on page 45, but even though it's problem 45, you look at number 2 for the answer because of the superscript 2. So this is the answer that we should get, and they don't give you all of the answers in the back of the book, so this is just for part B, so we can check that when we're done. Okay, so I'm going to start off by looking for the electric field at point A, which is here. And I can use this equation that we saw on day 1. So I have the electric field is equal to KQ over R squared in the R hat direction, because this is a one-dimensional problem. R squared in the R hat direction. Okay, and I'm going to do this for each individual charge and then add all the electric fields together. I'm actually going to do this in one step. Let's call this electric field A because it's for point A. That's equal to the electric field from charge 1 plus the electric field from charge 2 plus the electric field from charge 3 plus the electric field from charge 4. I could write all of those out separately, but I'm going to try and solve it all in one line. Okay, so I start off, this is charge 1, 2, 3, 4. So starting off with charge 1, all of these charges have a charge of either plus E or minus E, again, like we saw in lab. So this charge is minus E, so this is K times minus E over the distance from the charge to the point of interest from here to here is 1 block, so that's over A squared. And r hat goes from the charge to the point of interest. From the charge to the point of interest is pointing in the positive I hat direction. So that's I hat. So this is electric field 1. Then we move on to charge 2. This charge is E, so that's plus K times E. It's also 1 block away, so that's A squared. And the vector r hat goes from the charge to the point of interest. From the charge to the point of interest here is going to the left. That is in the negative I hat direction. So this electric field is pointing to the left because the charge is negative even though I hat is positive. This electric field is pointing to the left because r hat is negative even though the charge is positive. Then we move on to charge 3. That has a charge of negative E, so this is K times negative E, and we are 1, 2, 3 blocks away from the point of interest, so that is 3A squared. Make sure you square both the 3 and the A. Going from the charge to the point of interest is in the negative I hat direction. Then, for the last charge, that is 1, 2, 3, 4, 5 blocks away. The charge is E, so this is K times E. We said we were 5 blocks away, so that's 5A squared. Going from the charge to the point of interest is in the negative I hat direction. Okay, so let's simplify this a little bit. In each term, I have a K and an E over an A squared, so let's pull that out. KE over A squared. And then I'm going to pull out an I hat also and put that at the end. So what I'm left with for this first term here is a negative 1. That's minus 1. Same thing for the second term here. For the third term, I have a negative sign and a negative sign, so that's positive. It's divided by 3A squared. 3A squared is 9A squared. I already pulled out the A squared. So that is plus 1/9. And this is negative. We have 1 over 5A squared, which is 1 over 25A squared, and we pulled out the A squared, so that's minus 1 over 25. And then if you pull out your calculator and you calculate what we have in parentheses here, that is negative 1.93. Okay, so finally I need to calculate K times E over A squared. Because these are ions, we know that the absolute value of the charge is equal to E, and E is equal to 1.6. We used 1.6 in lab. I would like to use 1.602 times 10 to the negative 19th in my calculations here. But if you want to use 1.6 instead, you can do that. K is 9.0 times 10 to the 9th newtons times meters squared per coulomb squared. So this is 9 times 10 to the 9th newtons times meters squared per coulomb squared times E, which is 1.602 times 10 to the negative 19th coulombs, divided by A squared. A is 1.41 times 10 to the negative 10th meters squared. Okay, so if I plug my numbers in there, I should get negative 1.40 times 10 to the 11th. For homework, if you give me 3 significant figures for your answer, I should always be happy with that. You can check your answer. Well, you can't check your answer in the back of the book for this one because they only have the answer for part B. This is negative 1.40 times 10 to the 11th. Let's just check to make sure that the units work out here. So I have meters squared divided by, this is going to be meters squared in the denominator, so the meters cancel out. This is newtons per coulomb squared now times coulomb, which leaves me with 1 coulomb. So that's newtons times coulombs in the I hat direction. And this is the electric field for point A. I'm going to write it again down here. The electric field for A is equal to negative 1.40 times 10 to the 11th newtons per coulomb in the I hat direction, and box that, and then say, by symmetry, the electric field at point C is equal to negative 1.40 times 10 to the 11th newtons per coulomb in the I hat direction, and box that also. I don't have to show any work for this. That was the point of answering the question up there. So I'm good with point A and with point C, and now I can look at point B. The electric field at point B is equal to the electric field at point B from charge 1 plus the electric field at point B from charge 2, plus the electric field from charge 3, plus the electric field from charge 4. Again, you could write all these out separately, but I'm going to try and do it all at once. Okay, so now I'm at point B, which is at the center of my diagram here. I'm going to start with the charge which is all the way to the left. That is a negative charge, and it has a charge of negative E, so that's K times negative E, and I am 1, 2, 3 blocks away from the point of interest, so that distance is 3a squared. And then we have the vector r hat, which goes from the charge to the point of interest. From the charge to the point of interest is in the positive I hat direction. And then we move on to charge 2. The charge is E, and it is 1 block away, so that's plus K times E over a squared. From the charge to the point of interest here is in the positive I hat direction. Then I move on to charge number 3. So I have plus K times the charge, which is negative E, divided by the distance squared. We are 1 block away, so that is a squared. The unit vector r hat always goes from the charge to the point of interest. From charge 3 to the point of interest B, that vector is pointing in the negative I hat direction. So that's minus I hat. And then for charge 4, that is 1, 2, 3 blocks away, and the charge is E, so that's plus KE over 3a squared. Going from charge 4 to point of interest B, that vector points this way, so r hat is equal to negative I hat. Just like I did up here, I'm going to pull out a KE over a squared. For this term, that leaves me with a negative 1 over 3 squared. Remember that you have to square both the 3 and the a, so that's minus 1/9. I'm going to put the I hat at the end. If I pull out a KE over a squared from the second term, that just leaves me with a 1. And I have 2 negative signs in the third term, so that also leaves me with a 1 when I pull out the KE over a squared. And for the last term, we have a negative sign and a 1 over 3 squared, so that is minus 1/9. And if you plug into your calculator, negative 1/9 plus 1 plus 1 minus 1/9, you should get 16 over 9. I guess I decided to do that because that is just 1 minus 1/9 is 8/9, and 1 minus 1/9 8/9, so that's 16/9. Okay, so we have K, which is 9.0 times 10 to the 9th newtons per coulomb, times 1.602 times 10 to the negative 19th coulombs, divided by a squared, and a is equal to 1.41 times 10 to the negative 10th meters squared, and that gives me 1.29 times 10 to the 11th newtons per coulomb in the I hat direction, and this is the electric field from point C, and I can, whoops, that's the electric field from point B. And I can box that, and then if you look on the last page of this section for answer number 2, They say the electric field is 1.3 times 10 to the 11th. I got 1.29. It rounds to 1.3. So if your answer, if you round it to two significant figures, if it agrees with what's in the back of the book, then you are correct. Okay? A few comments before we move on. When I do the calculations here, I'm not actually plugging it into my calculator, and I'm not always doing it in my head. I have actually done it ahead of time. So if I make a mistake in the problem, like let's say I forgot to square that, it is possible that I'll still write down the correct answer because I'm not actually plugging it into my calculator as we do the problem. So you might find it helpful if you pause the video so that you can do the work on your own, because I'm doing it faster because I don't have to plug everything into the calculator. Okay? So you should be following along and writing everything down as I go. You can go at your own speed, use the pause button if you need more time, and that concludes problem 45. Also, I guess you might be interested in knowing that it says 41 at the bottom of the page because this is an old version of the textbook, but is actually problem 45 in your textbook. Okay, so you can ignore the numbers on the bottom of my page here. I'm going to be going by the problem numbers which are in your textbook. Okay, so that concludes problem 45.